Hi, this is the second part on the series of video about complex numbers. If this is the first time you're viewing this video, don't forget to hit the subscribe button so that you'll always be updated with my latest lesson. For this video, we're going to discuss algebraic properties of complex numbers. At the end of studying the lesson, the students are expected to prove basic algebraic properties of complex numbers and the complex operations addition and multiplication, and perform subtraction and division of complex numbers. So, if you're ready, halina't matuto. Let's start with the properties of complex addition. At this point, it should be clear that complex addition is a closed operation, meaning if you add two complex number, then the result is another complex number. So we discuss here the properties of adding two or more complex number. The first property A1 is associativity. For any complex number C1, C2, and C3, we have the following. Quantity C1 plus C2 plus C3 is equal to C1 plus the quantity C2 plus C3. So this tells us that if we change the grouping symbol from C1, C2 to C2 plus C3, then equality still holds. To show property A1, we need to show that the left-hand side quantity C1 plus C2 plus C3 is equal to the right-hand side quantity C1 plus C2 plus C3. To do this, we are going to use the definition of addition. First, let C1 equals x1, y1, C2 equals x2, y2, and C3 equals x3, y3. Starting from the left-hand side, we are going to substitute the values of C1, C2, and C3. And then, using the definition of addition, we're going to show that the left-hand side is equal to the right-hand side. So the left-hand side, which is equal to C1 plus C2, quantity plus C3, can now be written as C1 is the complex number x1, y1, plus C2 is the complex number x2, y2. Those quantity plus C3 is the complex number x3, y3. Now, using the definition of addition, we can combine the complex number x1, y1 and x2, y2 by adding the real part x1 plus x2 and adding the imaginary parts y1 plus y2. Let me rewrite x3, y3. So we now have two complex number. Applying again the definition of addition, we can get the sum of these two complex number. The real part is x1 plus x2 plus x3. The imaginary part is y1 plus y2 quantity plus y3. So we're able to write this as a single complex number with real part x1 plus x2 quantity plus x3. But since now these are all real numbers, and real number is associative, meaning we can regroup addition from x1 plus x2 to x2 plus x3. For the imaginary part, we have the quantity y1 plus y2 plus y3. Again, since these are just real numbers and addition of real numbers is associative, then we can regroup this from y1 plus y2 to the quantity y2 plus y3. Reversing the definition of addition, we can split this into the sum of two complex number with the first complex number having the real part x1, y, and the imaginary part y1. So for the first complex number, we have x1, y1. And for the second complex number, we have the quantity x2 plus x3 for the real part and y2 plus y3 for the imaginary part. We have x2 plus x3 and we have y2 plus y3. So that's our second complex number. But again, that second complex number can still be split into two complex number or sum of two complex number. So let me rewrite x1 and y1 for the first complex number. And then for the second part, we have x2, y2 plus x3, y3. So the second number was written as the sum of the two complex numbers, x2, y2, and x3, y3. But observe that x1, y1 is simply c1. On the other hand, x2, y2 is c2 plus x3, y3 is c3. And this is exactly the right-hand side. And this completes the proof of the first property. The second property, A2, is existence of additive identity. There exists an element O called the identity element in the set of complex number such that for all complex number Z, C plus O is equal to O plus C is equal to C. Later we'll see that O is actually the complex number 0. In the point of abstract algebra, the identity element O is the 0 element in the set of complex number. Meaning, this is the element where given any complex number, the sum C plus the 0 element is the same as the element C. We claim that this 0 element is actually the complex number 0, 0. So all we need to do is now to show that this equation holds C plus O is equal to O plus C is equal to C. Let's start with C plus O. Again, we're assuming that C can be written as the complex number xy. So C plus O is the same as the complex number xy plus the complex number 0, 0. Using the definition of addition, we have x plus 0 for the real part and y plus 0 for the imaginary part. Going inside the components of the complex number, we have x plus 0 which is the sum of the real numbers x and 0. But 0 is the additive identity in the set of real number, meaning x plus 0 is equal to simply x. Similarly, y plus 0, again 0 being the additive identity in the set of real number is simply y. X plus y is simply the complex number c. So we were able to show that c plus o is the same as c, where o is the complex number 0, 0. Similarly, if we start with o plus c, so we have o plus c is equal to the complex number 0, 0 plus x, y. Again, applying the definition of addition of complex number, we have O plus X for the real part and O plus Y for the imaginary part. So, we have 0 plus X, 0 being the additive identity in the set of real numbers. So, the real part becomes X and the imaginary part, 0 plus Y becomes simply Y. And still, that's equal to C. So, we're also able to show that O plus C is equal to C. And we are done. The third property A3 is existence of additive inverse. For each complex number Z, there is an element C star called the additive inverse of C, for which C plus C star is equal to C star plus C is equal to O, or the additive identity. So basically, C star is the number for which when we add to C, the result is 0. Given a complex number C, we want to show that there is an element C star such that when we add the two of them, either C plus C star or C star plus C, the result is the additive identity 0, 0. Let's see denote the complex number xy. For this complex number, we want to find the complex number C star. For now, let's denote C star by the complex number AB. So we want to find the value of A and the value of B such that when we add C and C star, the result is 0. So we have C plus C star is equal to the complex number xy plus the complex number AB. And we want this to be 0. So this would imply that on the left-hand side, we have adding xy and AB we have x plus a for the real part and y plus b for the imaginary part, which we want to be the zero element 0, 0. So that implies that the real part x plus a must be equal to 0 and the imaginary part y plus b must also be equal to 0. These are now two equations in real numbers. So that means we have a equals the negative of x and b equals the negative of y. So that means the real number c star is simply the complex number negative x, negative y. Because of this, we can now use the notation negative c for the complex number negative x and negative y, and we call the complex negative c as the negative of the complex number c. Just like in the set of real numbers, the additive inverse of the complex number is the negative of that complex number, which can be derived by taking the negative of the real part, negative x, and taking the negative of the imaginary part, negative y. Now, we have an idea of what C star should be. According to the previous result, C star should be negative x, negative y. We want to show that indeed C plus C star is equal to C star plus C is equal to 0. So we have C plus C star is equal to the complex number xy plus the complex number negative x, negative y. Using the property or the definition of addition, we have on the left hand side x plus the negative of x for the real part and y plus the negative of y for the imaginary part. Working on the components, the real part is x plus negative of x, but in the set of real numbers, x and negative of x are inverses of each other, which means x plus negative x is equal to 0, and similarly, y plus negative y is equal to 0. So we were able to show that C plus C star, where C star is negative x, negative y, is the zero element O in the set of complex number. Similarly, one can show that C star plus the complex number C is also equal to 0. And I'll leave that as an exercise for you to work on. The fourth property, A4, is commutativity. For any complex number C1 and C2, C1 plus C2 is the same as C2 plus C1. To show commutativity, we will use the same technique as before. We will show that the left-hand side is equal to the right-hand side. So let C1 equals the complex number x1, y1, and C2 the complex number x2, y2. The left-hand side is equal to C1 plus C2. And plugging in the values for C1 and C2, we have x1, y1 plus x2, y2. Using the definition for addition of complex number, we have the real part x1 plus x2 and the imaginary part y1 plus y2. Again, working on the components of this complex number, we have the real number x1 plus x2. But since the set of real numbers is commutative, this can be written as x2 plus x1. Similarly, the imaginary part can be written as y2 plus y1. And then we can split this complex number as the sum of two complex number, with the first complex number now being x2, y2, and the second complex number now being x1, y1. So we were able to write this as the sum of C2 plus C1, which is the right hand side. And so we are done. So to make sure that you understand the lesson, be sure to answer self-check test number 2. Answers of the self-check test are found on the last page of the module. For complex multiplication, we have the following properties. Again, it should be clear that complex multiplication is close in the set of complex numbers. Meaning, if you multiply two complex numbers, then the product is again another complex number. So start with associativity. For any complex number C1, C2, and C3, the product C1, C2 quantity times C3 is equal to C1 times the quantity C2 and C3. Same as the addition, we can regroup multiplication. We can transfer the grouping from C1 to C2 to C2 and C3, and the product is still the same. To show associativity property, we will use the same technique as before. We will show that the left-hand side is equal to the right-hand side. So let C1 equals the complex number x1, y1 and C2 equals the complex number x2, y3 while C3 equals the complex number x3, y3. So we have the left hand side equals C1 times C2 quantity times C3. Plugging in the values of C1, C2, and C3, we have the quantity x1, y1 for C1 times x2, y2 for C2. And then multiplied to x3, y3 for C3. We work first x1, y1 times x2, y2 since it's inside the grouping symbol. So using the misfoil method, we have x1, x2 minus y1, y2 for the real part, and x1, y2 plus x2, y1 for the imaginary part. Then this complex number is multiplied now to x3, y3. Again, another application of misfoil, we have first x1, x2 minus y1, y2 times x3. Last, we have minus quantity x1, y2 plus x2, y1 times y3. So this is the real part. For the imaginary part, we have outer, this one, times y3. So we have x1, x2 minus y1, y2 times y3 plus inner. So this one times x3. We have the quantity x1, y2 plus x2, y1 times the quantity x3 for the imaginary part. Simplifying, we get x1, x2, x3 minus x3, y1, y2 minus x1, y2, y3 minus x2, y1, y3 for the real part. For the imaginary part, we have x1, x2, y3 minus y1, y2, y3 plus x1, x3, y2 plus x2, x3, y1. On the other hand, if we compute the right-hand side, we have C1 times the quantity C2 times C3 is equal to the complex number x1, y1 times the quantity x2, y2 times x3, y3. This time, we start with x2, y2 times x3, y3. So let me copy y1 x1, y1 first, and then inside the grouping symbol, we multiply using misfoil. So that's x2, x3 minus y2, y3. Last, so for the imaginary part, we have outer x2, y3 plus inner y2, x3 for the imaginary part. Another application of multiplication of complex number, we have for the real part, first, that's x1 times the quantity x2, x3 minus y2, y3. Last, we have minus y1 times the quantity x2, y2 plus x3, y2. This is y3. For the imaginary part, we have outer, so that's x1 times this quantity here, x1 times x2, y2 plus y2, x3 plus inner, so that's y1 times the quantity here, y1 times quantity x2, x3 minus y2, y3 for the imaginary part. Simplifying, we get for the real part x1, x2, x3 minus x1, y2, y3 minus, so let me write x first, x2, y1, y3 minus x3, y1, y2. For the imaginary part, we have x1, x2, y3 plus x1, x3, y2 plus x2, x3, y1 minus y1, y2, y3. Now, comparing this to the result we get from the left-hand side, we see that they are exactly the same. And so we were able to show that the left-hand side is equal to the right-hand side. And we are done. Second property, M2, existence of multiplicative identity. There exists an element I called the multiplicative identity in C such that for all complex numbers C times I is equal to I times C is equal to C. Multiplicative identity in C is the number such that when you multiply to any complex number C, the result is the same complex number C. The multiplicative identity in the set of complex number is actually the complex number 10. So for complex number C equals xy, and for the complex number 10, we want to show that C times I is equal to I times C. Plugging in the components xy and 10 for C and I respectively, we have xy times 10. Applying the definition of complex multiplication, we have x times 1 minus y times 0 for the real part. For the imaginary part, we have x times 0 plus y times 1. Looking at the components, since x times 1 and 1 times 0 are real numbers, and in the set of real numbers, 1 is the identity element for multiplication, so we have x times 1 equals x, y times 0 is 0. So the real part is simply x. For the imaginary part, we have x times 0 equals 0, and y times 1 equals y. So we have y as the imaginary part. And this is just the complex number C. So that means C times the complex number 10 is equal to C. Similarly, as an exercise, you can show that I times C is the same as the complex number C. So you just have to give the details of the proof. So we have as the multiplicative identity the complex number 10. For simplicity, we will just denote the multiplicative identity as the number 1 and the additive identity as the number 0. Third property, M3, existence of multiplicative inverse. For each non-zero complex number C, there is an element C to the negative 1 called the multiplicative inverse of C, for which C times C to the negative 1 is equal to C to the negative 1 times C is equal to the multiplicative identity 1. For a non-zero complex number C, we want to find another complex number denoted as C to the negative 1 such that their product becomes the multiplicative identity 10. So let's see equals the complex number xy, which is not the same as the zero complex number. For now, let's denote C to the negative 1 as the complex number AB. We want to find the complex number AB such that when we multiply C and C inverse, we get the multiplicative identity I. Or that means when we multiply xy and AB, we get the complex number 10. Applying multiplication of complex number on the left-hand side, we get XA minus YB for the real part and XB plus YA for the real part. And we want this to be equal to the complex number 1, 0. Now, for these two complex number to be equal, their components must be equal. So that means XA minus YB must be equal to 1 and XB plus YA must be equal to 0. So now we have a system of equations with two unknowns. The unknowns here are A and B. So we can solve this equation either by elimination or by substitution. Let's try elimination. We want to eliminate one of the variables A and B. So let's try to eliminate first the variable B. To eliminate the variable B, then the coefficients of B must be the same with opposite signs. So this is negative YB. On the other hand, we have XB. So for them to have the same coefficient with opposite signs, we need to multiply this by X and this by Y. So we multiply the first equation by X. We have X squared A minus XYB equals X. On the other hand, if we multiply the second equation by Y, we have XYB, so that's plus XYB times Y squared A equals Y times 0 is 0. Now, if we add these two equations, we are left with X squared A plus Y squared A equals X. Or, solving for A, we have A equals X over the quantity X squared plus Y squared. On the other hand, if we want to eliminate the variable A, since we have XA here and YA here, we need to multiply the first equation by Y and the second equation by negative X, so that the coefficients becomes equal but opposite in sign. So we have, for the first equation, XYA minus Y squared B equals Y. For the second equation, we have negative XYA minus X squared B equals 0. Again, adding these two results to negative Y squared B minus X squared B equals Y. Now, if we divide everything by negative x squared minus y squared, we can solve for b, which is equal to negative y over x squared plus y squared. So that a is equal to x over x squared plus y squared and b equals negative y over x squared plus y squared. So for a non-zero complex number C, represented by the components x, y, the inverse of C, or the multiplicative inverse, to be exact, is the number with real part x over x squared plus y squared, and imaginary part negative y over x squared plus y squared. Fourth property, M4, commutativity. For any complex number C1 and C2, C1 times C2 is equal to C2 times C1. This is similar to the commutativity property of real numbers, wherein the product of two real numbers, R1, R2, is the same as R2, R1. Now, if we combine the operation, multiplication and addition of complex number, we have the following rule: distributive property of multiplication over addition. If we have three complex numbers, C1, C2, and C3, and we want to find the value of C1 times the quantity C2 plus C3, all we need to do is to distribute C1 to C2 and C3. That is C1 times C2 plus C1 times C3. Now, this is fairly easy to show, and I will leave the proof as an exercise. Okay, it's your turn. So, try to answer self-check test number 3. Prove that for any complex numbers, C1 and C2, C1 times C2 is the same as C2 times C1. This is the commutative property of multiplication. Next, prove the distributive law of multiplication over addition. That is, C1 times the quantity C2 plus C3 is equal to C1 C2 plus C1 C3. If you want to check the answer to self-check test, you can go to the last page of the module where the solutions are presented. At this point, we can now proceed to complex subtraction and division. Subtraction is actually an operation derived from complex addition and additive inverse, while division is an operation derived from complex multiplication and multiplicative inverse. Let's start with subtraction. Let C1 equals x1, y1 and C2 equals x2, y2 be complex numbers. The difference C1 minus C2 of complex numbers is defined as C1 plus the additive inverse of C2. So that is C1 minus C2 is equal to C1 plus negative C2. In elementary operation, this is actually how we do subtraction. We change the sign of the subtrahend, then we proceed to addition. Looking now at the components of C1 and C2, and since the additive inverse of C2 is negative x2, negative y2, then we can rewrite C1 minus C2 as the complex number x1 minus x2 for the real part and y1 minus y2 for the imaginary part. On the other hand, if C2 is not 0, then the quotient C1 over C2 of complex numbers is defined as C1 times the multiplicative inverse of C2. Very much like the definition of subtraction, we first get the inverse of the second number and then we proceed with the operation multiplication. So that's C1 times the multiplicative inverse of C2. Now, looking at the components of C1 and C2, since C2 is not the zero element, then we can get the multiplicative inverse of C2 as follow. For the real part, we have x2 all over x2 squared plus y2 squared. And for the imaginary part, we have the negative y2 all over x2 squared plus y2 squared. Now, using this value, we can compute for the product x1, y1 and the multiplicative inverse of C2. And so, we have this quantity. Now, this is cumbersome to memorize. So, what you can do is you can simply get the inverse of C2 and then proceed with the actual multiplication of C1 and the inverse of C2 instead of memorizing this formula. Let's have some example. Let C1 equals negative 2, 3 and C2 equals 4, 2. We want to find C1 minus C2 and C1 over C2. For number 1, we have C1 minus C2, or that's the complex number negative 2, 3 minus the complex number 4, 2. So all we need to do is to perform component-wise subtraction. So we have negative 2 minus 4 for the real part and 3 minus 2 for the imaginary part. So we have negative 2 minus 4 is negative 6 and 3 minus 2 equals 1. For number 2, C1 over C2, or it's equal to the complex number negative 2, 3 over the complex number 4, 2. Following the rule for division, all we need to do is to multiply the numerator 2, 3 to the inverse of the denominator 4, 2. Again, inverse is defined as if z is represented by the complex number xy, x over x squared plus y squared for the real part. For the imaginary part, negative y over x squared plus y squared. In this case, for the complex number 4, 2, we have 4 over 16 plus 4, that's 20, comma, negative y. So that's negative 2 over 20. Or to simplify the operation, negative 2, 3 times 4 over 20 is 1 over 5, negative 2 over 20 is negative 1 over 10. So now, to perform the multiplication, we use this FOIL, negative 2 over 5 minus negative 3 over 10. So that becomes plus 3 over 10. For the imaginary part, we have last. That's equal to negative 2 times negative 1 over 10 or positive 2 over 10 plus the inner is 3 times 150 or 3 over 5. To simplify further, we have for the real part, let's make it over 10. So this is 10 divided by 5. 2 times negative 2, negative 4 plus 3. For the imaginary part, we have over 10. 2 plus 10 divided by 5 is 2 times 3, 6. Or that's equal to negative 4 plus 3 is negative 1 over 10. 2 plus 6 is 8 over 10, or that's 4 over 5. So that's how we subtract and divide complex numbers. If you want to check if you understand how to compute the difference and the quotient of complex number, be sure to answer self-check test number 4. Solutions of self-check test can be found at the last page of the module. Okay, that's it. So, for the next video, we're going to discuss the geometry of complex numbers. Hope to see you there.